Hello, you're watching this video because you're thinking about doing A-level physics. Well, you've made a good choice. What I'm going to do is go through just a few basics across a few videos to try and get you prepared for year 12. Right, well, standard form will be a good friend of yours if you choose to do A-level physics because it makes things a lot easier. At GCSE, you'll already be familiar with kilo or kilo, as in kilometre. Okay, so 1 times 10 to the 3, so 1,000 metres is 1 kilometre. You'll also be familiar with milli, as in millimetres, okay, which is 1,000th of a metre, so 1 times 10 to the minus 3, which is 0.001. Okay, from biology, you might also be familiar with micro, which is this Greek letter mu. Okay, that's 1 times 10 to the minus 6. Okay, and then the rest is something that you're probably new to, or at least you haven't seen for a while. Okay, so going up the scale, we've got 1 times 10 to the 3, which is kilo, 1 times 10 to the 6, which is mega, the same as a million, and that's a capital M, which is different from your lowercase. Giga, which is a small g, is 1 times 10 to the 9, and tera is 1 times 10 to the 12. You come across these in various different aspects, so terahertz here. You come across gigapascals when you're talking about Young's modulus, etc. Okay, so that's going up the scale. Going down the scale from milli, which is 1 times 10 to the minus 3, micro, which is 1 times 10 to the minus 6. You've got nano, okay, which is a very, very small measurement, and we'll look at nanometers in a short while. You've got pico, which will be useful for when we look at capacitance in year 13. We actually, at A-level, go down to femto as well, which will be 1 times 10 to the minus 15, which is lowercase f. And that's when we're looking at the radius of a nucleus. So let's have a look at an A-level example. Okay, now we know that white light, when you put it through a prism, disperses and splits up into different colours. The different colours have got different wavelengths. So I know from my work in optical physics that the wavelength of red light is 632 nanometers approximately. Wavelength, of course, being from peak to peak in between a wave. Okay, so 632 nanometers, 632 times 10 to the minus 9, or if you prefer, 6.32 times 10 to the minus 11 meters in standard form. Okay, we know from our GCSE that V equals F lambda, so that's wave speed equals frequency times wavelength. That changes to a C at A level for wave speed. Okay, same thing. Okay, we also know that all waves travel at the speed of light being 3 times 10 to the 8 meters per second. Of course, the C standing for wave speed, and also being the C in E equals mc squared, so c squared being the speed of light squared. If we have a look at the wavelengths of anything on the EM spectrum, okay, as the frequency increases, the energy increases proportional to each other. So when we go from radio to gamma, okay, gamma has got short wavelength, which means it's got high frequency, which means it's got high energy. Okay, the proportionality constant is h, so if you use your gradient, that value of h is Planck's constant, which is 6.63 times 10 to the minus 34 joules seconds. Okay, this is why standard form is important, because we do not want to be writing out a load of zeros. So if I wanted to calculate the energy of red light, what I would do is I would substitute this into that equation, where the f would disappear. F equals wave speed divided by wavelength. So h times by c divided by wavelength would give us 6.63 times 10 to the minus 34, which is here, times by the speed of light, which is here, times by the wavelength of light that is red, which is 632 times 10 to the minus 9, which means that red light has this amount of energy, which is 3.2 times 10 to the minus 19, also known as 2 electron volts, but that's for something later. Toodles!